this talk is going to be about structured concurrency. So this is taking some ideas of concurrency and then applying some structure to them, I guess. So that's where we're going to go. There's a project that this is based on that I started working on a little over a year ago. We're going to go through that, see a lot of different code and a lot of different programming languages. Because I'm going to be throwing a lot of different types of stuff at you, just feel free to stop me if you have questions as I go, so we don't have to wait till the end. Lately at AWS, I've been working on MCP stuff, the new hot thing in the world of AI, and I wrote a blog post just recently about MCP. That's that QR code is for that blog if you're interested in what's going on with MCP. So that's kind of my recent stuff. But let's dive into structured concurrency and start talking about that. Okay, so what is structured concurrency? You all probably know what concurrency is. Structured concurrency, it implies that it is applying a structure to how we do concurrency. Well, what is the actual structure? It is essentially a hierarchy. So what we're going to do is we've got some like main task, you've got, let's say, your main program, whatever, and then you're going to define a scope, and the scope is going to allow you to then spin off child processes that are attached to this parent scope. And then what you're going to do is there's different ways that you can manage how those tasks complete. But in the simplest form, we'll wait for all of those tasks to complete. And once all of them have completed, then we will say, all right, our parent scope is now completed. And that will then be the end of that scope. So it'll end the scope once all of the tasks, concurrent tasks within that scope are completed. But you can see the kind of hierarchical nature to it because each child task can then also be a parent of other children, and you can essentially have as deep of a hierarchy of concurrent things running as you want. But the important part is the scope that is managing the life cycle. And so we'll talk about cancellation and some of the features that we get and error handling, some of that as we dive in. But the important part is that there's a parent with children, and that defines the structure of structured concurrency as this hierarchy. So that's our kind of basic overview of structured concurrency and the actual structure of it. But there's some use cases of structured concurrency which are pretty common. The most common is what's called a race. And this is not a race like the bad kind of race condition that you don't want. This is a race that's actually very useful. It's a race like a horse race. So in a horse race, what you're going to do is you're going to, hit start. You're going to start the race, and your horses are going to go. And then at the end of the race, there's a winner. Who gets across the finish line first? And so that's what we do with structured concurrency to define a race, is we've got our parent scope. We have our children that we've spun off. That can be as many children as we want. And in the easy kind of default form of a race, as soon as one of these children wins the race, we cancel all the other children in the race. So an important part of structured concurrency is the ability to cancel anything that is a concurrent operation. If we cancel the parent, that'll cancel all the children, but we can also cancel any child. And that should ideally cause it to be destroyed immediately and no longer take up any resources, essentially detaching it from the outer scope. We're no longer waiting for these things to finish. As soon as they're done. So that's where the horse race analogy kind of falls apart, because as soon as the first horse gets to the finish line, we don't just kill the rest of the horses or cancel them. That would be mean. We let them actually try to finish the race. So a little bit different than your normal horse race, because we are actually ideally with a race going to cancel the children that are the losers. So sorry, you didn't make it across the finish line first, you're canceled. Okay, and then as soon as that one winner is across the finish line, then our parent scope is going to finish with the value from the winner. So that's our basic race, which is one of the most useful things that we typically do in structured concurrency. There certainly is value of doing structured concurrency with this type of thing as well. If you want to fan out to a bunch of things, but then get all of the results from all of your children, that's a typical structured concurrency operation as well. But the race is definitely one of the more interesting, useful uses of structured concurrency. Okay, so that's our basic race. But there's some things that hopefully are the way that we're using structured concurrency and doing a race. There's some things that hopefully we'll just get for free and automatically. So the one thing we've already talked a little bit about is loser cancellation. Hopefully, if we've got a good kind of library to do structured concurrency in, hopefully loser cancellation is just built into it, and it does that thing where it cancels the children who didn't get across the finish line first. We'll see some examples where that's not the case. Okay, resource management. So ideally, when we have these child scopes, ideally they are resource managed. So if it has to open a resource and then close a resource, it shouldn't matter if it was canceled. It should still be able to close the resource, that sort of thing. So we'll see some examples of how to do that and how that works. We should also hopefully have efficient thread usage. So in a system with structured concurrency, we don't want to use a actual operating system thread generally for each child. We want to have something that is managing the actual underlying threads in a more efficient way so that we can do lots of parallelism, lots of concurrency, and not have that tied to actual operating system threads, which are pretty expensive. So there's some different approaches for how that's managed, and we'll talk a little bit about that as we go through some examples. Timeouts are usually an important part of structured concurrency. Is I want to have some amount of time that I expect this thing is going to take, and if it doesn't finish in that amount of time, I want to be able to easily cancel the whole scope if I reach that timeout. And then errors as losers. So let's say that, going back here, that we'll talk about this more in detail in a minute, but let's say that this task creates an error. You should be able to choose what happens in that case. Do I want it to be considered a loser and for the race to continue? Or do I want, as soon as I get an error, for that to be considered a reason to stop the whole thing and get to the bottom and say, hey, I'm done, but I finished with an error. So we'll get some examples of that later. But those are hopefully things that come for free when we're using a structured concurrency library. Okay, so we'll see examples of all that in a little bit. So the project that I mentioned that I started building a while ago is called Easy Racer. And the idea of Easy Racer was I'm going to have some structured concurrency obstacle course things that we're going to see how different languages, different frameworks, different libraries can tackle essentially different obstacles in structured concurrency, and then see how they compare, see how the programming model is different, see how hard it is to do certain things. So I created this Easy Racer, and it's a server. And what you do is you try to accomplish this task. There's 11 of them, and then there's different implementations of the client that actually try to do those obstacles. And so this is the non-exhaustive list. I think we're up to 20-something different languages and frameworks to show how structured concurrency can be done with different languages and libraries. There's some Scala ones, there's a few Java ones, there's Kotlin ones. Somebody contributed some OCaml ones for me. There's Python ones, C#, Rust. And so lots of different options for how to look at how these different tasks are handled, or obstacles are handled. So what I'm going to do is go through some of the obstacles that exist and then show you some of the different implementations with different languages and different libraries, just to give you a sense of the different ways in which structured concurrency is dealt with depending on your language, your framework, that sort of thing. Okay. In general, in structured concurrency, I think there's kind of 3 different approaches that are taken for creating that parent scope and then managing the lifecycle underneath it. And so the first style, and we'll see code examples of all this in a minute, is what I'm calling like direct style. And with direct style, you as a developer don't have to think about the actual scope. It just gets created and defined and managed for you based on the kind of the hierarchy that's implicit in your code. And so we'll see some examples, but this is probably, when you look at the code examples that I'll show you, the direct style is the most concise, most kind of expressive to the problems that we're trying to solve. Doesn't necessarily mean it's the best. There's trade-offs across all these different approaches, but it's going to be the most concise code examples that we see. Then there's a style called what I'm calling scope-driven. Scope-driven is where we manually manage the scope, where we're going to create a parent scope, we're going to manually add things into the scope, and then define a way for what the exit condition of that scope is. And it's all done kind of manually through calling APIs. And then the third option is called effect-oriented, and these are using effect systems. I've got a whole nother talk tomorrow about effect systems where I'll dive deeper into what effect systems are, but we'll see some of the code for effects and different approaches to that as we go through today. So those are kind of our three broad categories of types, approaches to structured concurrency. But let's dive into some of the code. So for the first scenario, I call them scenarios in Easy Racer. The first scenario is the easiest one. It is just this very simple where I want to race two HTTP requests. So a very kind of basic example of a race. I've got a server, and what the client needs to do is make two concurrent connections to that server, and then there's going to be one of those connections that responds back to the client and says, hey, you got the right answer. And then the other one is the loser, and it should get canceled. And this particular scenario doesn't verify that the cancellation actually happens. There's another one that does that. But it does get you to, you have to make the two concurrent connections to the server, and then to get the right answer, you have to get the response that was essentially the first one that returned a response back to you. So let's take a look at some implementations of this basic race. So the first one, I'm going to show Scala because I think this is maybe one of the most concise implementations of this particular scenario. It's using a library called aux, which is the direct style for doing structured concurrency in Scala. And this is based on Java Loom, so it's based on virtual threads. It does really require virtual threads to be able to do what it's doing underneath the covers to manage the actual scope. So you don't see anything in here about scope or the parent or the children or the cancellation or the error handling. All of that is essentially managed implicitly. This race success is actually the only piece of aux that we see here. So what we're going to do is, I'm getting my URL. I'm going to make an HTTP request. You'll see that this one is a def, so this is a function called rec. And the reason why I made this a function, not a val, is because I want to call it twice. So both of those right here in this race success, I'm going to call rec twice, and I want it to actually make two requests. And so race success is this feature of aux that's doing all of the structured concurrency for us. So I want to actually run this one so that you can actually see what it looks like from kind of a debugging perspective. So there's scenario one for the Scala aux example, and you'll see the code that I just showed you. But let's run this thing. I do have my server for Easy Racer running locally. It's a Docker container, so I just got Docker running. It's not displaying anything yet, but it will. And so my Docker container is what I'm going to have this client actually make the request to. Okay, so let's just run this thing and see what happens here. So I'm only running this scenario one function in this case, but we'll see once it compiles and runs. So here's my make request where we're printing out that we're making a request, and then that's where we actually make the request. But you'll see that we do see that, hey, we're making a request, we're making another request, and then the response that I got back from this race success was just one value, which was the HTTP response body from the winner. The loser got canceled, so it went away, but we do see the response called right. And if we look over at the Docker container logs, we'll see that, let's see if I can make that any bigger. I don't know how to make it bigger. So scenario one, we're seeing that the server, my Easy Racer server, is printing out number of concurrent connections 1, and then it gets to 2. And as soon as it gets to 2, my server then responds to one of those requests and says, hey, you're the winner. You got the right answer. And then you'll see that we do go down to 0 connections, meaning that once the race had finished, then the cancellation did happen, which closed the connection to the server. So that's our very basic race and easy implementation of doing that with, in this case, the Scala aux library. Okay, let me pause there before I go on. Any questions about basic races or any of this so far? Yeah.
How to make
Yeah, let's go back to this one. Okay, so this is, we don't have a third task, we only have two. But what's happening sequentially is we've spun off these two concurrent tasks. And you can see that in the server log, seeing that, yes, there were two concurrent connections to the server. So we have two HTTP requests open to the server. And then one of those connections, and my server is managing this lifecycle, but one of those connections returns an HTTP response. And as soon as that response comes back, that then is completing this child task. So the request getting the response is the task essentially. And so as soon as we get that response back, then the race says, all right, hey, race is over. Now cancel all the other children. And so in my case with the Easy Racer server, this second task actually never will respond. It actually just will sit there and do nothing and not actually send a response forever. And so when we saw the server go down to 0 connections, we actually know that sure enough, as soon as we got this task completed, it did in fact cancel that second request, which closed the HTTP request from the client side. Was that helpful to explain that? Okay. Yeah, go ahead. Yeah, so like why would we do a race? What would be the benefit of doing these things? So good question. I should actually have some of the actual use cases for races. So here's one that's pretty typical. Let's say that I've got a database and then I've got a cache. And it could be that operationally, I may want to make a request to both my database and to my cache and race those two things together. And likely the cache is going to respond faster, but maybe it was a cache miss, whatever. And so maybe for some reason the cache is taking longer. And so it could be that the database is actually going to respond faster than my cache. And so why not race those two things? And whichever one comes back first, great. If it's the database, we'll go and update the cache maybe. But that is just one example of a place where people do these races. There's other ones like, let's say in the new world of AI, you're hitting inference, you're doing inference to an inference server for an LLM. And you maybe are going to like do some load balancing across two different models. You're going to use Sonnet 3.7 and OpenAI or something like that. And so you may actually want to make requests to both of those and then see whichever one starts responding faster, then choose that one, close the other one. So anytime where you're trying to decrease the latency by having two or more different things that can do the same thing, that's a good place for a race. Was that helpful for use cases there? And we'll talk about a specific form of a race later that where this gets used most often is in something called a hedged request. We'll talk about hedging in a little bit. Yeah.
Yeah. What you
Yeah, so it is different in that it's managing this scope for you. It's managing the cancellation. It's managing the error propagation. So it is it's a higher level API than your like standard fork join. We will see in the Java example that I'll show in a minute that there's some semantics that are very similar to fork join, but the key difference is this like managed scope, the thing that is able to do the cancellation where and propagate, do things like races and propagate cancellation, that sort of thing. So so it's the hierarchical structure that is added on top of our basic concurrency stuff. Yeah. Yeah.
my I understand that I'm going to pick up the first one and other responding. But the second is already registered for the content, right? So if you're canceling it, the work done, how we can convert to the cancel of the action. And I take the key is kind of, possible.
Yeah.
The key in the data resistance. So I'm not, but I'm not wanting to what it's done.
Yeah, so I think typically these sorts of things are done on non-mutating types of actions, because if it was a mutating action, then you would need to come up with some way to reconcile, like, okay, I don't want to add the same record to the database twice. And so typically this would be used on kind of read operations, not on write operations. Maybe there's some other ways that you could also do this for write operations, but I think most often this is races in particular are used for read operations, or maybe most of the structured concurrency uses are for read operations. Yeah, good question though.
Yeah.
Okay.
Yeah.
For Java? Yeah, let's get into Java. Good segue here. Okay, so we saw the Scala Ox one, direct style. Let's look at another direct style with Rust, and then I will get to Java in just a minute. With the Rust one, we've got our function that's going to make our request. It's an async function. And then in this one, what we do is we just create a list of our futures, and then we call futures.next and then await that. And that .next is what's going to actually do the race for us. So this is in a whilelet and pattern matching on a sum with an OK. But this is the basic kind of direct style in Rust for how we would do a basic race. There's another quick one I want to show you, which is using a popular library in Rust called Tokyo. And with Tokyo, we got the request, but then there's a macro in Tokyo that gives us a little bit nicer syntax to be able to do this race, where we're going to put both of our requests in, and that's all we need to do for the Tokyo one. So Tokyo is pretty nice with that macro, but there's some trade-offs to that macro we'll talk about in a little bit. Okay, so that's the Rust one. Python, this one's interesting because Python actually was one of the, as far as I know, one of the earlier implementations of structured concurrency was done in Python. And so it uses the scope-driven approach. And the scope-driven approach is this, we've got our request, but what we're going to do is create a task, but then we need to put those tasks, you'll see that we're putting them into this async IO wait. And so this, there were other implementations that were called like a nursery, and the nursery was like the parent scope. And so we'd put our tasks into a scope, and then we could wait for the task to be done. And when it's done, we're going to cancel the losers. So there's a bit of manual work here where we're manually kind of managing what goes in the scope and manually managing what to do when the scope completes, when we get our value out. And this is actually kind of similar, at least in concept, also scope driven to the Java Loom one. So this is a new API. I couldn't remember if it still is in preview or not in Java. But to do a race with structured concurrency on top of Java Loom. So with Loom, we get the virtual threads underneath the covers. So we get that efficiency of being able to not have the thread per request kind of thing going on. But what we're going to do in this is we're going to create a new structured task scope. We'll talk about the shutdown on success in a minute. But then, very similar to what we talked about earlier with fork join, is we're going to fork tasks into the scope. And then we're going to do a join. And this scope.join is where things are going to essentially wait. And because it's virtual threads, we're not really waiting in the traditional sense. We're not just like blocking threads here. It's a virtual thread, so it's okay if we just wait right here. And then as soon as we get one of these tasks that's been forked in the scope to complete, then we're going to continue on to the next line where we actually pull the response body up. So that's our Java example, scope driven. So we're having to kind of manually manage the scope and what we put into it and how we wait for the things to be done in that scope. So not as kind of verbose as the Python async IO one, but there's a little bit of boilerplate here for managing the scope, especially when compared to something that was really designed to not have you manually manage scopes like this one. But yeah, this is good. That's scenario one. I'll pause there and see any questions about any of these other implementations so far. Yeah. That's right. So as soon as this join finishes, which means that there was a winner in the race, then it will cancel the other tasks. So yeah, that gets managed for you. Yeah, that's a good question. So in the case, and this could be done with anything, like I'm just using HTTP here as an example. So I think maybe a better example for this will be, let's say I'm going to make a query to a database. And that query may take a very long time to finish. It's a complex query. And so database drivers, as well as HTTP clients, have the ability to say like, hey, I need to cancel this. And so stop doing whatever work you were doing. And so there is cancellation built into most of these protocols that allow us to essentially say like you might be midway through what you're doing. I need you to stop now. And so in the case of HTTP, the way that happens is the client will actually disconnect. And so there is the ability for when you make an HTTP connection to just like close that connection from the client side. You can also close it from the server side if you want, but essentially what's happening on cancellation here is the client side is closing that connection to the server. Yeah, good question. Priority. So it is 100% based on time. And so so they both happen concurrently. They're both there, which is why virtual threads is important, so that we are actually executing these two things at the same time. But then as soon as one of those gets a response, as soon as that happens, that then completes the scope and cancels the other children. So there isn't really a way to do prioritization because it's all fully concurrent. Yeah, good questions. That's the next scenario that we'll go into is error handling. Yeah. Okay, so that's scope driven. There's effect oriented is the last approach that I wanted to show for this one. There's a library for TypeScript called effect. And with effects, which again, got to talk in more detail tomorrow, but what we do is we create an effect. So this is a value rec, and then we do effect.race with two recs, and that's going to do our race just like we've seen in other ones. So that's using the TypeScript effect library. There is a Scala library called Zio, which is also effect oriented. See, pretty similar to what we saw with the effect one, a little bit more concise syntax. But in this case, what I do is I take my first rec, which is the effect, so it's not actually running yet. I race it with another rec, and then this .run is what actually is going to essentially call this, make the first rec and the second rec happen inside of a race. So that's Scala Zio, different way to do things with effects. Yeah, go ahead. Yep. Yep. So if you have two database queries, are they in a race? Like you're racing the two queries against each other?
I think so.
You really to be a race or use structured concurrency, you really do have to have a scope. So you have to have that parent scope, which I'll go into this one. You have to have that scope that you're spinning off kind of both concurrent things in that scope. If you don't have a scope that's managing children tasks, then it's not going to use structured concurrency. To be structured concurrency, you really need the scope. Was that answering that? Cool. Okay, so just to recap, we've got some task, and I'm saying main task, but it could be anything. It could be even another parent scope. The thing that defines our structured concurrency is having a scope, creating concurrent children in that scope, And then in the case of a race, as soon as we get a winner of the race, we're going to cancel the other children. And then the value that we get out of this parent scope is the result of the winner. So that's our basic race. Let's go on to scenario 2 in Easy Racer, which is great. We're going to do something very similar to what we did in scenario 1. We're going to race 2 concurrent requests. But in this case, as soon as we open those 2 concurrent requests, one of those is going to close from the server side. The server is going to say, close, I'm done. And so this will trigger the client side to produce an error, because typically with an HTTP client, if the server just like hangs up on you, it's going to cause an error on that request. So this could be an exception if you're in Java, or other approaches, depending on the language. But this scenario, when we make those 2 concurrent requests, one will be an error. And so what this scenario tries to show is how does your structured concurrency manage that the race that has an error in it? And so what this one looks like, and back to this diagram, is that this child task 2, let's say that it produces an error. What do we want to happen in that case? There's 2 different things that you can usually choose from for what to do in the case of one of your children producing an error. This one is where we're going to say shut down on success. What that means is that our parent scope will complete once we get to a success. So this error is just considered a loser in the race, but our horse fell over, it didn't reach the finish line, but the race is still going, right? And so we're still going to wait until one of these children completes with an actual result before we will complete the parent scope. So that's shut down on success. And that's going to be, I think, the most typical way that you're going to handle errors is errors. They're just losers, and that's okay. Things can lose, and we're going to continue and wait until we get to a complete. But there is the other approach, which is called shut down on error, usually. And then with shut down on error, what we're going to do is say, as soon as we do get an error, we're going to consider the race to be done. All right, I'm sorry, but a horse died, and everyone else, the race is now over. And so we're going to then cancel all the other children that are in the race. This gets really disturbing talking about horses this way. I'm sorry. I come up with a better analogy for races. Okay, so we got an error. We're canceling the children, and then the scope is completed, but it is completed with an error instead of the result that we were hoping we would get from the race. So that's the shutdown on error. So let's take a look at what this looks like in some different languages and frameworks. So first is the Java Loom one. And actually, this looks exactly like scenario 1. It's the exact same code with the exception of now I'm calling /2 on my server instead of /1. But this is the part that I skipped over, this is where we're specifying how to handle errors. And just like on scenario 1, we specified shutdown on success. There is also a shutdown on failure, I think it's called, which would give us the other behavior where things would close as soon as there's an error. But for this scenario, we actually want to consider the thing that gets closed, the connection that gets closed, to be a loser and keep the race going in that case. And so that's what happens. That's the same code that we saw before. Okay, so that's our scenario 2 in Java with Loom. Pause there. Any questions on that one? Yeah. Yes. So there is a Go implementation of it. I think there's 2 Go implementations of this. Definitely go check those out in the Easy Racer repo on my GitHub. I will say that their Go was one of my least favorite ones for structured concurrency. And you can go look at the code and see why. There's some things that get pretty messy with cancellation and error propagation. And so yeah, go check out the code if you want to see why. But it does reveal that I don't think Go's strong point is structured concurrency. I think there are other good things about Go. Structured concurrency, I don't think is one of them.
I think normally I'm gonna write something later
Yes.
I'm not in like that's not
Yeah, so let me show you. I think it's the next one. I'll show you this one. In this case, the cancellation is just implicit, happens implicitly. But there are other things like in Kotlin coroutines, and I like Kotlin and I like coroutines, but like Go, managing the cancellation is not one of the stronger suits of Kotlin and coroutines. So this is what I came up with to do scenario 2 in Kotlin. There isn't really exactly a race, a high-level race with Kotlin coroutines. There's a select, and then I have to give it my 2 tasks. But then if I put my client.get into a try block, and then I await cancellation because I don't want the race to end. So this is simulating the what's it called? Shutdown on success. I'm trying to simulate shutdown on success, where I'm saying, like, don't stop the race because I got an error. So I do this await cancellation, and I do that for both of them. And then I have to like wait, clean up my children at the end. So I showed this at a presentation, and somebody was like, "Oh, you have a deadlock in your code, or a potential deadlock in your code." And one of the things that structured concurrency is trying to do is make it so that you don't have deadlocks. That should be this higher level abstraction that, it makes it so you don't have to think about a lot of the nasty, harder parts of concurrency. So I was like surprised. I was like, okay, what is the potential deadlock? And I want to show you this because what I did was I went to my AI code assistant, and I said, is there a possible deadlock in scenario 2? This is using the Amazon Q one. But the LMs are amazing. You should use them because it actually does a pretty good job at looking at my code, the code I just showed you, and it's going to tell me about the code. Hey, here's your code, blah, blah, blah. But then it's going to say, yeah, there is a potential deadlock here. The potential deadlock is, what if both of the things that you're racing, what if both of them produce errors? And then you're just sitting there waiting for something to actually succeed with a value, but all of your racers are dead, and so we can't continue, so we just deadlock. So it's pretty cool that the LLM identified that issue, my deadlock in that code, and explains it to me. So I haven't. I think I started fixing it and didn't ever finish because it started to get a little bit nasty. But that's where, when you have these libraries, like the Java Loom one, it should manage these things for you. And sure enough, as we can see from scenario 2, it does manage it for us. And so this is where we see some of the benefits of structured concurrency, is like, take care of those details of concurrency that are hard. Take care of those for me. And that's where we start to see a lot of the value of structured concurrency. So not one of Kotlin and coroutines kind of strong notes. There is a Kotlin library called Arrow that does have a good race implementation that does a much better job of this. And there's an implementation of Kotlin with Arrow in the Easy Racer repo if you're interested in that. But just raw coroutines in Kotlin, not super awesome at a race, especially one where there can be an error. Okay, show you another implementation. This one with Scala and a framework that uses something called algebraic effects. And this one's called Kio. And I like Kio. There's a lot of really interesting things about it. It's effect-oriented, but I really love the conciseness of this. So this is scenario 2. So one of those connections is producing an error. I think this code is the exact same for scenario 1. Yeah, it should be the exact same for scenario 1. But nice, concise, doing all those things, the management of the errors, the cancellation, all those things for us. And this is where structured concurrency can be pretty awesome at giving us the ability to do do concurrency in a way that is concise and gives us all the benefits that we don't have to manage the underlying gory details of concurrency. Okay, moving on to scenario 3. So with scenario 3, what we have is essentially scenario 1, like scenario 1, where we race 2 things, do that, but now do it 10,000 wide. So make 10,000 requests to the server. And this is where you better have virtual threads or some really efficient way to manage the actual threads, because you have to actually open 10,000 concurrent connections to the server in order for this scenario to pass. And so with this one, let's look at some of the different implementations. This is the Java Loom one. And this one, very straightforward, very similar to what you've seen before. I'm just going to 10,000 times do a scope.fork and make a request. So I'm just putting the same thing that you saw with doing it twice. I'm now doing it 10,000 times. And then I do the same scope.join. And all that because it's Loom and virtual threads works great, right? 10,000 concurrent requests and everything's happy. So that's the Loom version of the 10,000 concurrent. Pause there. Any questions on that one? Yeah. 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 Why would you want to put 10,000 concurrent connect requests into anything? I don't know if there's a good use case for 10,000, but it was a good way to show that virtual threads are important. But for just a race in general, yeah. So anytime that you can do the same thing concurrently, and you want to choose the thing that is the fastest, that is the primary reason why you would use a race. So there's a lot of different scenarios where you can do the same thing. And I named a few examples earlier, but essentially at its core, if you can do the same thing concurrently and you want to pick the fastest one of those, then that's where you use a race. And so there's lots of different scenarios where that makes sense, but it's not something like not everyone in this room may need a race, right? Like it's not something that everyone's going to need in every application.
What?
Yeah.
Out of curiosity, what trigger you like? What project were you working on? Like you use the race and you were like, okay, let's try out a certain language handle it. So it was give us the motivation that.
Yeah. Yeah. So this spawned. Let me come back to that when we get to hedging, because hedging is one of the more interesting uses of this, and so hedging was one of the primary motivations for that. But we'll get to hedging in a little bit. Yeah.
Then like we do some.
Yeah. So yeah, good question. So usually we're not going to make the request, like in this kind of scenario, we're not going to make the same request to the same server. Oftentimes what we do is we have a load balancer, and the load balancer is going to send these requests to different servers. And part of the reason why we may want to do a race across two different servers is that maybe one is bogged down, it's running slowly, and we want to deal with the potential that that's going to happen. And so we're going to send it to two different servers, potentially through a load balancer, to allow us to do a race to get the fastest response. So I think it's a little convoluted in my easy racer that I'm sending these requests to the same server, when in reality, you probably want to send them to different servers because you're looking for like where operational things may vary because of network paths, because of latency, because of server load. There's lots of different factors that can be impacting the kind of operational latency, but the race is going to give us the ability to essentially disperse those requests so that we can get to the lowest latency, or potentially the lowest latency. Okay, this is the Java JOX one. I haven't showed JOX yet, and if you're doing Java, JOX is a really good structured concurrency library. It's based on the aux one that you've already seen from Scala, but JOX for Java. And so it's got this really concise structured concurrency API. So kind of a little, it's more direct, like the Scala aux one that we've seen a few times. It's that direct style. Java JOX is also the direct style, where you see I'm not having to manage the scope. I'm not having to fork things and join things. It's all just direct and built in. So in this case, all that I'm doing is creating a list of callables of HTTP responses of strings, and I'm creating 10,000 of those. Okay, so I've got my list, and then I call race with all of those, and that then is going to make the 10,000 requests based on Loom and do all the things we've been talking about with structured concurrency for me. So nice, concise one there with Java JOX. Okay, that's scenario 3. Let's see. How much time do I have left? We have what's that? 15 minutes. Thank you. Okay, right on schedule. Okay, let's go on to scenario 4. So for scenario 4, this is where we start to see some of the other kind of operational pieces to what should be built into structured concurrency. So with scenario 4, we're going to make our 2 concurrent requests, but then one of them should open, wait 1 second, and then close from the client side should close that one after 1 second. So we're going to put a 1 second timeout on one of our requests. And so now this is seeing how timeouts are going to impact our structured concurrency. So let's look at some examples here. In the Java Loom one, this is where we get into another depth of our structured concurrency, because the way that we assemble this is we're going to have our outer scope. So this is our kind of first parent. And then we're going to put into that, we're going to fork into that a task, but now we're going to have a new scope inside of that one. And that inner scope, what it's going to do is going to do the fork. And then there's an easy way in the structured task scope to do a timeout, which is we say join until. So I'm doing a join and I'm giving it the timeout that I want it to make. Wait for, that's 1 second. This is essentially the same thing as doing a fork with a thread.sleep, because what I'm doing is I'm doing 2 things in parallel to do a timeout. A timeout is really just a race against something that's going to wait for some amount of time and the thing you want it to do. So this is, I think, kind of syntactic sugar for essentially doing this race between a task and time. And when you're on virtual threads in Loom, you can do a thread.sleep, and that's not actually going to use resources. They're not going to lock up a thread. And so that's essentially the same thing here. So I've got this inner race that is racing my task against a amount of time. And so maybe my request comes back within the timeout, then it wins the race. Or maybe the timeout happens first, and then the timeout wins the race, and which will produce an error. And I'm using my shutdown on success, so that error will be considered a loser in the race. Okay, so I put that inner scope in as one piece to my outer scope, and then I make a request, just a regular request, as my other piece. So that's how we would, with Java Loom and structured concurrency in Java, would do the 1 second timeout. And so then, of course, the Easy Racer server verifies that, yes, I opened 2 concurrent connections. After 1 second, one of those gets closed, and then it responds with the one that wasn't closed and says, hey, you win. And if you get the right answer, then all good. Okay, so that's the Java Loom one. In some of the higher level, more direct APIs, we have a different way to do this. So this is very similar to what we saw before with Scala Aux, but in this case, we're just going to say, all right, timeout 1 second for our request. And that's how we would then have something happen that has a timeout around it. Again, based on virtual threads and Loom in this case for the Scala Aux one. Okay, so that's the Scala Aux one. Okay, any questions on scenario 4 and timeouts?
Yeah.
So again, think about a timeout as a race where you're racing something against time. And that's the point here. And then we can nest those things together. Yeah, Christian. Yeah, so definitely some of these concepts are related to reactive and get used together or in similar ways. So yeah, I think there's, like, if you look at the RX libraries, there's a lot of the same kind of concepts of adding timeouts to reactive things. So yeah, because I think reactive implies concurrency usually. And so yeah, I think you'll definitely see a lot of similarity between reactive stuff and maybe in some cases they're even the same thing. Like in the effect libraries, it all gets kind of munged together. It's like, yes, it's reactive and it's structured concurrency and all those things all at the same time. So yeah. Okay. That was scenario 4. So for scenario 8, here's the scenario. We're going to get into our race to concurrent requests, but this is where we want to see how resource management gets handled. Resource management being that I need to open a resource that's going to give me an ID back, some handle, something, and then I want to use that resource that was opened and then I want to make sure that I close the resource. So whether I was canceled or completed successfully, I want to make sure that that resource gets closed. And so we're going to see how this looks in different languages and frameworks to add resource management into this. So I want to start with Scala aux as the example here because it's a pretty concise one to show you what's happening. So we've got our request. Then we have 3 more requests. We've got a request to make our open request, which is going to get back an ID. We've got a use request, which is going to use an ID, make a request to the server. And then we've got a close request. So I did the open, use, and close all against my server as HTTP requests. It was kind of a little convoluted, but it was the only way that I could manage to make sure that the person was actually doing the open and close and that they were handling errors and all that kind of stuff. So kind of simulating what you would do in the real world, but probably you wouldn't do anything like this in the real world. Okay, so what I'm going to do is define a request response. And in the case of Scala aux, I'm going to say, all right, I'm in a supervised block. And supervised is what's going to manage the open and close of the resource for me. And so I say use in scope. So this is the Scala aux thing. I give it the open function and the close function. I think open is optional. Like if you don't have an open function, sometimes you only need a close, then you can leave that out. But I'm going to use in scope with my open and close. And what that's going to give me back is an ID that I get from my open, right? So open gives me a resource that I get back. And then I'm going to call use. So that's this one here. And so this is my function that's supervised, meaning it's going to manage that use in scope. This is using scoped values underneath the covers that we'll talk about in a little bit, which is another feature of Java and structured concurrency or Loom stuff in the JVM. And then finally, we're going to use the race success, and we're going to call 2 of those. So that all works. It completes the scenario. It does the open. In this scenario, I think one of the use requests actually returns an error in a non-HTTP 200, which is why we're verifying that I think this get right is going to verify that we got a 200 response. So one of those responses actually returns with a non-200 response, and it's going to verify that sure enough we did call close, even though that was a race loser and got canceled. So we want them to show that all those things are being managed for you. The resource management is being done correctly. The error handling is being done correctly. All those things are happening. So all that works in the Scala aux version. Let me show you the Java one. This gets a little more verbose because there's some of these higher level APIs don't exist, at least in like raw JDK land. But I'm going to have a auto closable called rec. I've got my different functions here for my open, my use, and my close. And then I'm going to have a way to store my ID. I make my open request on the constructor. I don't like that. Maybe there's a better way to do that. And then I've got a make call that's going to use my ID, call my make request, use request there. And then I've got my close function that's going to call my close request. So that's my rec class. So now when I want to use that, like we've seen before, I'm going to do my structured task scope, shut down on success. And then I'm going to fork. I'm going to do try with resources. Try with resources is what's going to give me the close when this thing ends, gets canceled or completes with the value. So I'm going to try with resources with my rec. I'm going to make my request. I do that twice and join them, which is going to give me the race essentially. And so pretty straightforward on how that one works, similar to what we've seen before, just with an auto closable and some state in there in the middle. So questions about that one, scenario 8?
Hi.
Okay. So resource management, great. We can make it happen in different ways. Okay. Save the best for last, which has come up a few times, which is hedging. So scenario 7 is one where we do something more practical with a race, which is called a hedge. And yes, sorry, go ahead.
Java
You could do it lots of different ways in Java. Yeah, I used auto closable in this case because I can do try with resources to manage the close. But yeah, lots of different ways to manage the resources. What's that?
Why did that?
Sure. Yeah.
That
You could possibly, yeah, maybe that would be the right way to do it is to be able to clean up any resources on close. Yeah, that'd be possible. Yeah, thanks for pointing that out. Okay, so hedging. So this one is where, I guess let me put it this way. Google uses request hedging in a lot of their infrastructure. And so back to the question earlier about what I was motivated by, I was thinking about how I was working at Google, and I was thinking about how Google in a lot of their infrastructure uses request hedging. The way that they use it is that a request comes in, and I think this is primarily for reading resources. Request comes in, and they kind of know what the typical latency of that request should be. So let's say it's 50 milliseconds. And so what they do in some cases is that request comes in, they wait that 50 milliseconds-ish somewhere, maybe they make it 40 milliseconds somewhere, but they relate it to their typical latency. And then if the response doesn't come back within that time amount, they fire off a second request. And so they do this kind of at the infrastructure layer where this is all just like done automatically for a lot of services. So they wait that like typical latency. And if they don't get a response in the typical latency, they're like, hey, maybe the server is dead. Maybe something went wrong. Maybe we're in a GC pause. Who knows? Something is not working as we normally expect it to. And so then they make a second request. And then they don't just close the first one because you don't know, like maybe the second one's going to end up taking longer. And so they race those two together. So like we've seen before with a race, it just is a race where one of the racers gets a start that is later than the first one. And so this is called hedging. And it's a fun and very useful scenario for races. So this is what it looks like in Scala Aux. We've got our request, but then when we create a delayed request, and because we're on Java Loom, we can just thread.sleep for 4 seconds and then make our request and then race those two. And that's a hedge, like super simple to define a hedged request. In this case, I've hard-coded what the expected latency is for this scenario, but you could imagine how in your infrastructure, you could have some expectations around expected latency and be able to base this on that if that's what you want to base your hedge on. Okay, so that's the Scala Aux one. The other ones are very similar to this, where it's pretty standard to be like, hey, wait for some amount of time, then make the request. And because hopefully you're on virtual threads, some efficient thread system, it should you shouldn't be blocking resources while you're waiting for that hedge. And the great thing is that because cancellation is part of structured concurrency, if I'm in this thread.sleep and this first request has won the race, then this one gets canceled, and I never end up even making that second request. It doesn't even get to this part, right? It doesn't get to the request part because I've just been in thread.sleep and I cancel the thread.sleep. All good. Move on. Yeah, it'll depend on how you're managing the scope. So this one, race success, is like the shutdown on success. And so it does depend on how you've defined for your scope to manage errors. Yep. Okay, let's talk about scope values real quick. How much time do I have left? Like a timer? 2 minutes. What was that? 2 minutes. Perfect. Okay. So scoped values. So you may be familiar on the JVM with thread locals. Thread locals are the way to store state on threads. That doesn't work when you're in a virtual thread environment. And so there's something that's part of Loom called scoped values, which allow you to attach state into a scope that is the scope we've been talking about with structured concurrency. And so they're immutable values. So once you put something into a scoped value, it can't change. You can always create child scopes that have new values, but once you have defined a value and run it in a scope, it's immutable. It is cleaned up automatically for you. So when the scope goes away, the associated value ends as well. And it's confined to the scope that you're in. So when you define a scope value and then execute something in that, that's the only place where you can actually then access that scoped value. So like thread locals, but in the world of virtual threads. So this is what it looks like. What we do is we define a scoped value. So in this case, I'm creating a new instance called my operation ID. Then what I'm doing is I'm saying scope value where. I'm giving it that scoped value instance. I'm giving it the value of that thing. And obviously this is just hard coded, but you could make that whatever. And then I'm calling something, which is what do I want to put into this? What do I want to run inside of this scope? So in this case, I'm running my scenario 7. And my scenario 7, what it's doing is it is making my request, doing my, let's see, this one's the hedging example. So it's doing the hedging. But let's see, is there anything not reading that yet? Okay. Oh, here it is. Send request. So send request is what I'm doing, using to actually send my request. And then that send request was down in a child in the scope, but then I can read. So you'll see the operation ID. So we're referencing that scope value and we're calling get on it. And that allows me to get the scope value out. So that's just an example. It's not, I need to come up with a better example, but this does show how you can have that state in your scope with structured concurrency and with Loom. So there's other ways to do it with different frameworks. I need to work on a new scenario for Easy Racer that'll actually require this to be used, and so we can see how it works in different languages and structured concurrency libraries. But that's it for that. Okay, to learn more, my GitHub repo for Easy Racer, where you can go see the Go implementations and all the other ones, is just on my GitHub, James Ward, and then called Easy Racer. There is a fantastic blog post that if you want to learn more about structured concurrency, it's called Notes on Structured Concurrency or Go Statement Considered Harmful. Really fantastic blog about structured concurrency. There's also another one by Roman Elizarov, who created Kotlin coroutines. There's a great intro with effects and concurrency and Zscheduler. JamesWard.com on my blog is where I'll post the slides. So if you want those, check them out there. Okay, I'll be around if you have other questions, but hopefully that was useful. Thank you.